Welcome back, everyone, online and in person. We are doing the equilibrium chapter. I wanted to mention very first thing off about class Wednesday, next class, is our visit to A-Lab, which is just literally like, 50 feet that way. It's in the same building. I sent an email around on Friday asking you to go on to Acorn to do the little survey box. And I think 6 people did it, which is like less than half the class. So if you haven't done that, please do that as soon as possible, just so I know who is interested in coming and who is not interested in coming. I think it'll be at a nice time just because we'll finish, hopefully, the equilibrium chapter today. And then that means we can have this happen as sort of a break in between this chapter finishing and then the next chapter that we're going to cover. Cool. Great. Yeah, I hope it'll be fun and change of pace and something a little different on Wednesday's class. What else is new? We got an assignment due tomorrow, like usual. That's the short one, just 10 questions. I'll post, of course, another assignment. We have a midterm coming up on March 3rd, I believe. And that is scheduled to take place during class time. So I'm not sure who's interested in writing it in person versus online. My plan would be for that, though, to make it open book. I don't want anyone either online or in person to have a disadvantage. So that's how I think about that. Sound cool? No strong feelings? If you have strong feelings and you don't want to express them here, just send me an email. So what we're talking about in this unit has been Le Chatelier's principle, which basically just says that if you perturb a system that's at equilibrium, it will shift left or right towards products or reactants to undo the effect of whatever shift you made. And we looked at a number of different ways that you could impact an equilibrium. We looked at increasing or decreasing the concentration of products or reactants. If you add reactants, that'll cause it to shift to the right to remove some of those additional reactants that you added. We looked at change in pressure, which is effectively changing concentration anyway. We looked at change in temperature, and we said temperature changes K. It also causes the equilibrium to shift to one side or the other, depending on whether it's endothermic or exothermic. So we looked at those examples. What else exactly? I think that was where we finished off, actually, looking at the effect of temperature. And we looked at how you can, if you know the delta H, standard delta H0 of a reaction, you can use that to predict what K will be at different temperatures. That was the Van Hoff equation. Maybe where we ended up. So we just have 2 more things we have to consider, how they'll impact an equilibrium. And the first one is adding an inert gas. So if you have a gas phase equilibrium taking place, and you add some inert gas, some gas that's not going to participate in the reaction, like nitrogen, any of the noble gases, something like that. If it's some gas that's not part of the equilibrium, adding that gas, it does change the total pressure, but it does not change the partial pressure of any of the gases involved in the equilibrium. So when we say gas phase equilibria will shift depending on the pressure, what we really mean is those equilibria will shift depending on the partial pressures of products and reactants. So adding an inert gas doesn't change that. So adding an inert gas will have no effect on the position of an equilibrium. So that's really all I have to say about adding an inert gas. No real effect on an equilibrium position. Second thing, which also has no effect, is adding a catalyst. Remember, a catalyst is something that we add to speed up a reaction. It lowers the activation energy or provides a new mechanism that's faster. Catalysts don't appear as reactants or products. They participate in the mechanism, but they're consumed in an early step and reproduced in a later step. So because they don't appear in the overall balanced equation, they also don't appear, they also have no effect on the position of an equilibrium. This is just maybe another example. While the catalyst changes the path, it doesn't change the initial state and the final state. And because delta G is a state function and K is just another expression of delta G, we wouldn't expect a catalyst to have any effect. So adding a catalyst will make an equilibrium establish more rapidly, but once it's established, whether the catalyst is there or not, it'll be in the same position. Great. Homework question. For the following reaction at equilibrium, it's the gas phase equilibrium, which change would cause the partial pressure of Br2 to increase? So the delta H here is positive, so it's endothermic. And so the way I would look at that is if it's endothermic, I would consider heat to be a reactant. So if we lower the temperature, essentially we're removing heat. That will cause this to shift to the left. So that will not increase the concentration of Br2. B, removing some NO. So NO is a product. If we remove the product, that'll cause the equilibrium to shift right. So that will increase Br2. So that will do what we want it to do. C, remove some NOBr. That'll remove reactant. That'll cause it to shift to the left. That will reduce the amount of Br2. Compress the gas mixture into a smaller volume. So what this will do is change all the partial pressures. What we want to do here is count the moles of gas on each side. So we have 2 moles here, and on the right we have 3 moles. Compressing this will cause it to shift towards the side with fewer moles, which is to the left, which will reduce the amount of Br2. That's not going to help. Adding a catalyst never causes the equilibrium concentrations to change. Good enough? Great. Yeah, B is our answer here. The last kind of piece of this equilibrium chapter that we're going to be looking at are solubility equilibria. And this is looking at solids that, when added to some solvent, typically we're talking about water, will dissolve to some extent. And back in Unit 1, in the first unit, you probably did looked at solubility charts where you could take a salt or you could take an ionic compound, and from that you could calculate, exactly, not calculate, you could, I guess, determine if something was soluble or insoluble. And those terms were very kind of broad because there's lots of things that are like slightly soluble that we would lump together with the insoluble group, and it's sort of the difference between soluble and insoluble. There's no definition. It's just it's like a sliding scale. If we use equilibria, then what we can actually do is, with much greater detail, define how soluble something actually is. We don't just lump it into 2 groups, soluble, insoluble. We say, this is exactly how much of this will dissolve under these situations. And that's an important thing, because some things are extremely insoluble, extremely low solubility, and some are, of course, much higher. Think about this, like when you go into a river, if you wade into a river, and you know how there's those like roundish river stones on the bottom, that's ionic compounds in those rocks. Clearly, like, there's water rushing over them all the time. Their solubility is extremely low. I've been doing work this last summer, with the TV show Curse of Oak Island. So I've been working with them and looking at water samples and things like that. And one of the things that, of course, they're interested in is gold underground. And the question came up: if there's gold underground, will you be able to see any gold dissolved in the water that's underground with it? In well samples and things like that. And it's an interesting question. What is the solubility of gold? And it's not 100% insoluble. It actually has extremely low solubility. So the amount that you can find in water is around parts per trillion. okay, which is a huge challenge. Like we're going to A-Lab Wednesday. They've got analytical equipment that can, in some cases, find minuscule concentrations of dissolved things. They'd have a tough time trying to find gold in water, even if there was a ton of gold sitting in a container of water for 1,000 years. So we're going to define solubility in terms of, we can call it either molar solubility, which is just how much of something will dissolve in a given amount of solution in moles per liter. We're also going to be using KSP. Sometimes you see solubility in grams per liter. We tend to prefer moles per liter in chemistry. Grams per liter you see more frequently in biology, when maybe the material isn't as well structurally defined. Like in chemistry, if we say NaCl, like we know what NaCl is, we know it dissociates in water to Na plus and Cl minus. But in biology, you might say like, you know, how many milligrams per liter of some protein is there? And we don't even know what the structure of the protein is, or chemical formula or anything like that. So it wouldn't make sense to use moles per liter if you don't even know what a mole is of that substance. So you might use grams per liter in that situation. So molar solubility is probably what we're going to be using most often, but just be aware that grams per liter is very common. Not just in biology, in medicine, often you see grams per liter as well. You see like solutions, like saline solution or different things like that. So yeah, both of those are real things, important. KSP is an equilibrium constant that we're going to define when you have a substance that is sparingly soluble in water or some other solvent. All right, so as I said before, we had these solubility tables, which, you know, lumps things into two very broad categories of soluble and insoluble. We know something like salt, if you put it in water, will dissolve to a pretty great extent. Sugar will dissolve to a huge extent in water. You can get a lot of sugar in water. Those are very soluble. But really, any substance, if you put enough of it into a solvent, will reach a limit at which it won't dissolve any further. We call that saturation. And so once a substance is dissolved to the point of saturation, and if there's still additional solid present that has not dissolved, there's an equilibrium that's established between the remaining solid and the ions or molecules that are dissolved in solution. All right, so you remember these solubility rules. I mean, I'm not testing you on these solubility rules, you're aware of them. All of these ones that are insoluble that you would determine from this table are actually sparingly soluble. So they're only soluble to a very small extent. Here are some examples: cadmium sulfide, lead sulfide, nickel hydroxide, aluminum hydroxide. So these technically insoluble, but that does not mean there's zero concentration of ions in these cases. Okay. All right, so let's look at an example. We're going to look at calcium carbonate. Calcium carbonate is what chalk is made out of, that you'd use on a chalkboard. Marble is also calcium carbonate. It's a major constituent of chalk and limestone rocks. It's slightly soluble in water when it forms the equilibrium that you see here. Calcium sulfate solid is in equilibrium with the constituent ions. Calcium 2 plus, carbonate 2 minus. And we would say that the KSP here is just the product of the ion concentrations, because on the left side, all we have is a solid. That solid is a pure solid. Solids, by definition, have an activity of 1. So we could divide it all by 1, but that's not going to change anything. This is where that little SP comes from. This stands for solubility product. It's the product of the ion concentrations. And that's, in this case, just calcium 2 plus times carbonate. So the math that we've already looked at so far to deal with equilibrium situations where we used ice tables and all of that, we can still use that for this same type of equilibrium. It's just a lot simpler. because typically there's no denominator. So the mathematical expression that you arrive at is just going to be a simpler situation. So these are maybe great ones to start with. Although, ironically, it's the last ones we're dealing with. So there you go. So yeah, we have KSP values, and the KSP value, the larger it is, that means the higher the concentrations of the ions at saturation. And so therefore, a large KSP means it's more soluble than something with a small KSP. So here we go. Here's some examples. And some of these numbers are extremely small. Like, look at this one, silver sulfide. Ag2S has a KSP of 6 times 10 to the negative 51. That's extremely small. Okay. Iron hydroxide, aluminum hydroxide are also very small, negative 30s. And then, you know, they range from 10 to the minus 6 all the way to 10 to the minus 51. Huge range that we see in these things, but none of these we would say are especially soluble. Silver sulfide, by the way, is what happens to silver if you have like silverware and you leave it out long enough. There's sulfur in the air that'll react with it, and it'll form silver sulfide on the surface, which is black in color. We call it tarnish. So when silver tarnishes, it's actually silver sulfide that's on there, and it can't be washed off. And if you look at the solubility, you can see why it can't be washed off. You can't soak that stuff off because it's so extremely insoluble. There's no way you can do that. So the only way to clean it off is you get like a special kind of, did you ever see this done before? It's like a paste almost, and you have to like kind of rub the silverware with it. And it's, I don't even know what's in the paste, but it would, I think what it does is it not oxidizes, it would reduce the silver back to silver 0. And I don't know what happens to the sulfur, but it chemically reacts it off rather than washing it off. Great, we're good. So write the solubility constant expression at equilibrium for each of these compounds. This is assuming that they are saturated. So aluminum hydroxide would look like this, AlOH 3 solid is in equilibrium with Al 3 plus, AQ plus 3 OH minus. That's the balanced equation. And so we would say that the KSP expression would just be concentration of the products, Al3 plus aqueous times concentration of hydroxide. And we would cube the hydroxide concentration because there's a 3 in front, just like we would. It's just basically the same as you'd write any equilibrium expression, except we leave out pure solids and liquids, which was always the case anyway. Next, we have lead fluoride, which is PbF2, solid, Pb2 plus, AQ plus, 2F minus, AQ. KSP, concentration of Pb2 plus at equilibrium. I guess there's an AQ in there as well. F minus AQ squared. Easy peasy, right? Nothing to it. Let's do an actual calculation. Calcium hydroxide slaked lime is a component of mortar, plaster, and cement. And solutions of calcium hydroxide are used in industry as a strong and expensive base. Calculate the molar solubility of calcium hydroxide in water if KSP is 6.5 times 10 to the minus 6. So what we're going to do is write the equation out, and we're going to do essentially like an ice box. Plus 2 OH minus AQ. And basically what we do is we start out and we have our initial change and equilibrium. So we're assuming we have a bucket of water that's pure, let's say a liter. We throw in enough calcium hydroxide to saturate the solution. And then we want to know how many moles of this has dissolved per liter. So what we would say is initially we have 0 of our ions, 0 moles. And we never care how much solid we have. As long as we have enough solid to saturate it, we could triple it, quadruple it, times it by 10. It's not going to make any difference to our final concentration of ions. So the change here, once it starts to dissolve, it's going to go up to plus X and plus 2X. And at equilibrium, we just have X and 2X. So our KSP is equal to 6.5 times 10 to the minus 6. And that's going to be equal to the concentration of Ca2 plus at equilibrium, concentration of hydroxide squared at equilibrium, equals X 2X squared, which is equal to 4X cubed. So now we just solve for X. We have 4X cubed equals 6.5 times 10 to the minus 6. X equals 0.012. Let me just double check. That's what I am supposed to have. Yeah. So that is X. That is the number of moles of calcium 2 plus that will dissolve in a liter. And because these have a 1-to-1 relationship, if you have 1 mole of calcium 2 plus ions, that means 1 mole of calcium hydroxide must have dissolved. So we would say the molar solubility then, S of calcium hydroxide, is that number, 0.012. Calcium hydroxide, actually, it's funny, throughout history, it's been a very important substance, mainly for construction, mortar, plaster, and cement. And this use of this compound has been known for a long time. And a few summers ago, we visited, my family and I went to Italy, to Rome, and we went to the Colosseum. And the Colosseum, apparently at its peak, had marble statues all through the Colosseum, these like amazing ancient art. And those are made out of marble, and marble is calcium carbonate. And they all disappeared after sort of the fall of Rome, and the Colosseum kind of went out of use. And actually it was like pillaged like crazy. And like the construction there, for example, held all the walls together using these big iron braces. And people wanted to melt the iron down to make tools and, you know, plows and stuff like that. So they like pulled all the braces off the walls, and it caused certain parts of the place to collapse. But what they did do is they took all the statues out. And if you take calcium carbonate and you heat it, what you get is calcium oxide plus CO2. And if you take calcium oxide and mix it with water, you get CaOH2. So what people did after the fall of the Colosseum is they stole all these statues and they cooked them down, they heated them up, and took the calcium oxide they got as a result, made calcium hydroxide, and used it for mortar and plaster and stuff like that to build other things. So kind of an expensive source material, I suppose, but people will make use of stuff. There you go. QSP versus KSP. QSP here has the exact same meaning when we talked about Q earlier in the unit. Q just means if you're not at equilibrium, or not necessarily at equilibrium, whatever concentrations that you have, you can stick them into the equilibrium expression and get a number. And that number will be the same as K if you're at equilibrium. If you're larger than K, you're past the equilibrium and you need to shift to the left. And if you're smaller than K, you need to shift to the right to reach equilibrium. So QSP is just sort of like a measure to tell you where you're at in an equilibrium situation, whether you're already at equilibrium, you're too far to the right or too far to the left. Nothing different here for QSP, except it's for this like sparingly soluble situation that we've talked about before. Great. So in the context of a saturated solution, just a plain old saturated solution where you have water and you have solids sitting on the bottom and you have, you know, what's happening is it's constantly dissolving away into the water, but it's also at the same time being deposited back into the solid. There's still action, there's still motion, there's still forward and reverse reactions. There's just no net change in the amount of dissolved material or solid material sitting at the bottom. So when QSP equals KSP, that describes the saturated situation, and it'll just stay the same way it is for indefinitely. For an unsaturated solution, that's when QSP works out to be less than KSP. It just means you haven't reached equilibrium yet. You have to shift to the right to make more dissolved products. And that just means it'll continue dissolving. So it means you're not quite there yet. I think about this sometimes, like for example, at home I have an espresso machine. And every once in a while, and I have to do this now actually, you have to descale the machine. And that's when you get typically calcium salts, calcium carbonate, and such things like that build up on the inside. And what you do is you make a solution of sodium citrate or citric acid. And you run that through, and that'll create an acidic environment that'll dissolve away the calcium carbonate. But what you do is you like dump a bunch of the solid in the water in the tank, and then you wait for it to dissolve. And it's always like a lot of it dissolves right away, and then it slows down, and then you still have solid in the bottom, and you're like, is this saturated and I'm going to wait here forever, or is this still going to gradually dissolve? It'd be great to be able to just test and know where you're at on the QSP there, which you could do if you had the equipment, but no one would ever do that. Right, so if Q is less than K, it'll shift to the right and more will dissolve. If Q is greater than K, you're describing a supersaturated solution where you have more solute dissolved in water than is thermodynamically stable. And one way or another, that's going to come out of solution and you're going to deposit a bunch of solid in there until you reach equilibrium, until you now have a saturated solution in there. So supersaturated solutions are probably the least common out of these three situations, but they definitely do happen. If you, sodium acetate, which is like NaCH3COO. Sometimes it's just NaOAC, sometimes it's just called. Sodium acetate is a flavoring material. They put in salt and vinegar chips to make them taste like vinegar. That can actually very easily make a supersaturated solution. And so what happens is you can dissolve this at a high temperature, let it cool down, and often it won't solidify back out again until you introduce some sort of imperfection. And the imperfection allows the crystals to start to form, and then it'll all at once form all these crystals quite suddenly. I know my mom had some eye issue going on where she needed to like apply heat to, and the eye doctor gave her these little like pads, and there's like a metal like strip in there that you can like snap back and forth, and then the rest was just like a little bag full of sodium acetate. And what you would do is you'd boil these things and it would dissolve all of the sodium acetate, so it'd be like a liquid in there, and they would sit like that, like you could sit like that at room temperature for hours and hours. But as soon as you like snapped the metal thing inside, it would start crystallization, and it would very quickly crystallize out. It would kind of make like a crunchy solid inside, not like super stiff, but And that process of coming back out of solution was exothermic, gave off heat, and it just warmed it just to sort of the perfect temperature. So she'd boil these every night to kind of reset them. And then when she needed to apply the heat, she would just snap it, put it on the eye, and then it would give off the heat. So yeah, that's making use of a supersaturated solution. Example, a solution containing 0.09 moles of lead nitrate is mixed with a solution containing 0.2 moles. Will it precipitate form? So I guess the question is, will this form a solid? Will this make a precipitate? So the way we would look at this is the precipitate we're looking at is PbI2. PbI2 solid would establish an equilibrium with its ion, which would look like Pb2 plus 2I minus. Those are both aqueous. And our Ksp would be equal to the concentrations of lead 2 plus at equilibrium times the concentration of I minus squared at equilibrium. So we know what that value is, right? It's given to us in the question. Small number, meaning this isn't very soluble. And what we want to do is realize that if we add that concentration of lead 2 plus, that concentration of I minus, this produce a solid. Well, we've gone past the saturation point. It's the perfect example of where we would want to use Q. So we could calculate our QSP and compare it to the KSP that we have there. QSP now, these look like they're the same thing. It's only the KSP, though, are only the concentrations when you're at equilibrium. QSP, that can be any concentration. So we don't know where we're at, so let's calculate QSP. 0.09, and it's in 1 liter. So that's 0.09 moles per liter. We don't put the units in to the KSP or QSP expression. I minus, we have 0.2 moles in 1 liter, so it's 0.2 molar. Again, we leave the units out. We square that. And what we end up with is 3.6 times 10 to the negative 3. Okay, so we calculated QSP, and we can compare that to our KSP. And hopefully you agree with me that the QSP here is a much larger number than the KSP. So because QSP is bigger than KSP, that means this is supersaturated. That means a precipitate will form. Funny, PPT is like commonly used as precipitate, but I realize it's also like a PowerPoint file. But no, precipitate will form because QSP is greater than KSP. Great. And just sort of an aside here, I don't want you to memorize that QSP greater than KSP means precipitate and so on. Like, you should really understand what this actually means, right? That if QSP, because of the QSP expression, if it's greater than KSP, it means the concentrations of your ions is too high. You've got to go back. It's got to form solid. Okay, common ion effect really is just kind of another application of the same kind of idea, KSP. It just means looking at KSP for situations where there's another ion already present in solution. Okay, so there's so here's an example. We have an equilibrium going on here between lead chromate with its ions, lead 2 plus, chromate ion. And this is sitting there nicely at equilibrium. What you can do if you added sodium chromate, which isn't itself part of this equilibrium, but because it's a sodium salt, it will dissociate to add more chromate to solution. So by adding solid sodium chromate, what you're doing is you're increasing the concentration of one of the products. That's going to cause this, due to Le Chatelier's principle, to shift to the left and produce more of your solid. So what you can do is add this solution of concentrated sodium chromate and precipitate out more solid. You can see where it's being added up here. You're getting all this extra solid form up at the top, which will eventually sink down. So this is just adding an ion through a separate compound that is common to that same equilibrium situation. So we can look at an example like this. A few examples ago, we calculated the solubility of calcium hydroxide in water. What's its solubility in 0.1 molar calcium nitrate? KSP is given to us again, 6.5 times 10 to the minus 6. If you remember before, the value we had for the solubility, S, of CaOH2 in water was 0.012 molar. So here's my question, first of all. Do you expect this substance to be more soluble or less soluble in a solution of calcium nitrate? Well, right away, you can kind of look at it and say, well, if the solution already contains calcium, we're not going to be able to dissolve as much, right? Because having that calcium ion present is going to push the equilibrium back towards solid, which means less is going to dissolve. So here's how we should handle a situation like this. We should realize the calcium nitrate using our solubility rules. We know that all nitrates are soluble. We know all acetates are soluble. All group 1 metal salts, like lithium, sodium, potassium, etc., they're all soluble too. Right, so if we have 0.1 molar calcium nitrate, what we should really be thinking is we have 0.10 molar calcium 2 plus, 0.20 molar nitrate. So when you see calcium nitrate, don't think of it as calcium nitrate. Think of it as a solution, calcium ions and nitrate ions, totally doing their own thing. Okay, so we're going to take our calcium hydroxide again. We're going to do the exact same thing we did last time. It's sparingly soluble. It's going to form an equilibrium where we have Ca2 plus Aq plus 2 OH minus AQ. We're going to do our ice. Once again, we don't care about the solid. We're going to assume there's enough to keep this saturated. And the only difference from before is our initial concentration of calcium 2 plus is 0.10 molar because we have the calcium nitrate to begin with. That one's 0. So it's got to shift to the right to produce some products. It's got to dissolve a little bit. It's got to produce some hydroxide. This will be plus X plus 2X, and at equilibrium, we're at 0.10 plus X and 2X. So again, we say KSP 6.5 times 10 to the minus 6 is concentration of calcium 2 plus, 0.10 plus X, 2X squared. And what we can do here is make the assumption, because this is a very small number, that simplifying assumption we wanted to make before, where if you take the K and you divide by the initial concentration, if it's greater than 400, you can ignore the plus X. We can do that here, and that's definitely going to be the case, that we can ignore the X. You can multiply it out. You'll end up with a quadratic equation, put it into the quadratic formula, and you can solve it that way. Or we can recognize that X is going to be a small number relative to the number it's being added to, the 0.1, and simplify this to be just 0.1 times 4x squared. equals 0.4 x squared. And then solving for x, we get x equals 0.0040 molar. And hopefully what you'll agree with me is that that is a smaller number than the solubility in just pure water. So that solubility is suppressed by having calcium already present in solution. Great. So if you get yourself in this kind of situation where you have a small x being added or subtracted from a number, you can use that simplifying assumption not just in the previous situations, but also in this situation as well. Perfect. We just have one very small piece of information left, and this is when we are doing solubility equilibria of metal sulfides. Metal sulfides are a little special. Remember, we talked about silver sulfide as being the tarnish that you get on silverware. I was just visiting a friend on Friday, and I learned that he has a silver dollar collection. And he's apparently has a silver dollar, a Canadian silver dollar from every year starting in like 1920. And he was like showing me them all. And there's like a period of like 6 years during World War II that they stopped making them because they needed silver for something else, and then started again. And yeah, he's big into it. None of them look tarnished though, so maybe he's got them stored in a special way. Metal sulfides. So if you had something like here, manganese sulfide, and its equilibrium with its ions, manganese 2 plus and sulfide 2 minus, that's how we would approach almost every one of these solubility equilibria, except the sulfides are a little bit special because the S2 minus is a strong base. That S2 minus will react with the water as soon as it's being generated to form HS minus and OH minus. And this is not an equilibrium. That's straight to the right because that's a strong base. We say it's essentially 100% complete when that reaction is done. So instead what we do is, because in this product there's no actual sulfide remaining, what we do is we express the equilibrium for this metal sulfide as the sum of these two chemical equations. So we cancel out S2 minus because it appears on both sides. And what we end up with is manganese sulfide plus liquid water is in equilibrium with the manganese ion, HS minus and OH minus in solution because of that base reaction. So our KSP then just becomes the 3 product ions there, manganese 2 plus, HS minus, OH minus, and we don't worry about the manganese MnS or the liquid water because both of those solids, liquids, they get activities of 1, don't appear in the overall equilibrium expression. Okay. I guess this would also be the case if you had an oxide. Like if you have something like, I don't know, FeO in equilibrium with Fe2 plus O2 minus. O2 minus is also a strong base. It'll react with water to make 2 moles of hydroxide. I think these situations are a lot more rare though, sulfides. Okay, last thing, write the KSP expression for each compound magnesium carbonate. We would say that its KSP is just Mg2 plus CO3 2 minus. There we go. Iron 2 hydroxide. Helping my daughter right now. She's in grade 11, IB Chem, and they're doing all this like naming of compounds, which is funny because I forget all the rules. I just like remember, I've seen enough of these enough times that I just kind of know what they are more intuitively, I guess. iron 2 plus, OH minus squared. Calcium phosphate, PO4, that would be a 2 and a calcium 3 to make the charges balance on that one. That's the other thing, is like memorizing all those complex ions. Like there's not a lot of them, I guess, but if you see enough of them enough times, can't help but memorize them. Same with molecular weights. Like you probably haven't thought much about memorizing the masses of the elements in the periodic table, and I have never like made an effort to do so, but I still memorize, I don't know, the 8 or so that are commonly used in organic chem, like hydrogen, carbon, nitrogen, oxygen, sodium. Sodium's easy. It's 22.99. That one is just interesting because sodium plus hydrogen plus oxygen, which is NaOH, is like exactly like 40.00. It's an easy one to remember. Ca 2 plus, aqueous cubed, PO4, aqueous 3 minus squared. Last, silver sulfide. KSP, you might just want to say this, Ag plus squared S 2 minus. That one's not right, is it? Sulfide reacts with water. It's not that. It is Ag plus AQ, still squared, HS minus AQ, OH minus AQ. So we have to write out for the sulfides only that it reacts with water in that way. Wonderful and fascinating. We are done the unit on equilibrium. We will begin the next one. We have, I think, 3 units left. So we're actually moving pretty well. We have an electrochemistry unit. We have an organic chem unit, and we have a unit on like, what's that one called? Phase equilibria, stuff like that. So we kind of have 2 more equilibrium kind of units. They're all based on delta G. And then the organic chem is just sort of like a fun chapter at the end, I guess. Not that these ones aren't fun chapters. They are phys chem, which is, yeah, some people's cup of tea, but maybe not everybody's. So we're done today. Wednesday, what I'm going to ask is people who are coming, we could meet in the classroom, or we can just meet, like, you know where I mean when I say like the study area with the bridge? Like if you walk out this door and go up the stairs, there's that big study area with all those seats. And then like on the opposite side from the windows, there's like a little bridge that goes across and there's labs in there. A lab is one of those labs. Maybe what I'll ask is for those that can come, that we meet in the area just outside, like where all the seats are. It's technically called the David Hustis Innovation Pavilion. And yeah, sound good? Or it's just simpler to meet here? You guys are hard to read. Anyway, I'll send an email and tell you exactly where to come. Please, though, fill out that, I mean, it's not filling out, it's just a checkbox. Fill out that little questionnaire I put up on Acorn. So please make sure you let me know what your intentions are for Wednesday, because how that will look exactly may change depending on exactly how many people are able to come. Awesome. Thank you very much, and goodbye to everyone online as well.